Hello BC students, it's your teacher. I'm making a video on something called arc length. So here's the question. Let's say you graph a function. Maybe it looks something like this. Say you're graphing y equals f of x. And you have maybe two x values. Here's a and here's b. One question that you're very used to is what's the area under the curve between a and b? And you know the answer to that. Here's a question I want to ask. So the question is, what is the length of the curve between x equals a and x equals b? So before you can even answer this, you have to talk about what do we mean by length of the curve. So for a straight line, it's really easy to tell what the length is. So what would we mean by length of this curve? Well, you sort of mean something like if you put a string up starting at x equals a, so starting at this point, and you were to sort of measure the length of the string, and then you could, once you get to b, you stop. Now this was the total length of the curve. You put this on your ruler, you measure it, and this is the length we're talking about. But to measure something with a string, that's not very mathematical. So we need to somehow make this process of measuring with the string, make this more mathematical. So humans, I said, are very good at measuring straight lines. So one thing we could try is we could try to go up here to the curve and put in some straight lines. So here I have a point P0, here I have a point P1, here I have a point P2. Now it's really easy to measure that straight line, the length of that straight line, and the length of that straight line. Well, you could do better by putting in more straight lines. So let me draw the same curve. Here's y equals f of x. Here's a, and here's b. Instead of using 1, 2, 3 points, well, you could use a bunch of points. 1, 2, 3, 4, 5, 6. So you have a P1, or P0, P1, P2, P3, P4, P5, P6. And you can just visibly see that here the little line segments are closer to the curve. So if you add up all the lengths of these line segments, you'll get a number that's closer to the truth. So you can probably guess what's going to happen here. Here we had just 2 line segments, so maybe in this case n is equal to 2. Here we had 6 line segments, so in this case n is equal to 6. So you can see, to get the mathematical definition of length, which is what arc length means, then we should take a limit. So that's what we're going to do next once I erase the board. Okay, so we're hoping to get a mathematical definition of arc length. Here's the setup. We have our curve, so I'm just graphing a function, y equals f of x. We have a starting point, x equals a, and an ending point, x equals b. So the idea that we had was we're going to put a bunch of line segments in here, n different line segments. We'll call the first one P0, P1, all the way up to Pn. And then you can see that if you add up the length of all these line segments, you'll get something that's close to the length of the curve. So what we're going to do is we'll define the length. So we'll define the arc length of the function f of x from x equals a to x equals b. This is sort of hard to write, so I'll just call this L. And then L will be the limit as the number n, so this n represents the number of line segments. I'll write that n is the number of line segments. Well, L, the curve length, the arc length, this should be the limit as n goes to infinity of what you get when you add up the length of all those line segments. So I'll say, I'll write the length of this first line segment as P0, P1 with a bar over it, P1, P2 with a bar over it, and then we go all the way up to Pn minus 1 to Pn, that's the last one. And we take the limit of this as n goes to infinity. Now you can also, if you want, you can write this with sigma notation. So this is going to be the sum from, say, I equals 1 up to n. So the first one goes from I minus 1 to I. So Pi minus 1 to Pi. Okay, so right now the goal is to sort of massage this and get this into something that's more recognizable in terms of calculus. So what we're going to do next is I will give each of these points coordinates. So I'll call P0, I'll call that x0, comma y0. I'll call P1 x1, y1. Say the general point, let's call it Pi, and Pi will be xi, comma yi. So this is just the distance of this line segment. Now think back to distance formula. So the distance between Pi minus 1 and Pi, well, the distance formula says this is the square root of the difference in the x values squared plus the distance in the y values. Okay, so we're going to put this expression into here and work it some more and hopefully get something. I needed some more room, so I erased this half and I put the most important things in blue over here. So L was our formula for the arc length. It involves a limit, and the goal is to make this nicer and easier to understand. And the last thing I wrote over on this side was the formula, using the distance formula, for the length of one of these line segments. So before we go any further, you need to remember something. This is a topic that you do not like very much. It's the mean value theorem. So what does the mean value theorem say? Well, it says if you look at something like f of xi minus f of xi minus 1 over x minus xi minus xi minus 1. So this thing right here, this represents the average rate of change of f on one of these intervals, say between xi and xi minus 1. Well, the mean value theorem says that this equals f prime of some special point c, maybe I'll call it xi star, just because. So that's what the mean value theorem says. It says that there is a point xi star that makes this true. And look, f of xi, well, that's just the same thing as yi, right? Y is the y value at the point xi. So this over here, the numerator, is just yi minus yi minus 1. So we have this expression equals this expression. So let's simplify it, clean it up. Let me bring the denominator over here. So this gives us that yi minus yi minus 1 equals f of xi star times xi minus 1. And the final thing I'll do to this is I will square everything. So you have no idea what I'm doing at this point. I'm just playing around with these expressions, but maybe you see it now. This thing right here is sitting right here. So what I'm going to do is I'm going to substitute in this longer expression into here because it will eventually clean up. So let's go there. So now I'll start from here. I'll use blue. So we have that pi minus 1 to pi, this length. Well, it's this thing under the square root. So I still have that first term. Now for the second term, I'll plug in this thing. So plus f of xi star squared xi minus 1 squared. What I want to do to make my life easier is I'll call this thing right here delta x. And it occurs here as well. Why do I want to call that delta x? Because what you have in mind is you're breaking up the x-axis into all of these points. So what I want to do is just let delta x be that difference between the 2 points. So this length here is your delta x. This is exactly what we did when we invented the integral. Okay, so how can I clean this up? Well, here we have a delta x squared term. Here we have a delta x squared term, so we can pull all of that outside of the radical. So inside the square root, you'll be left with, let's see, when we pull this out, we'll be left with 1 here. And for this one, we'll be left with f. There should have been a prime there. There should be prime here. F prime of xi star squared. And now we pull out this delta x. When you pull it out of the square root, it loses a square. So this right here is our formula for pi minus 1 to pi. All right, let me erase. Okay, so we're almost there. We almost have our formula. So I'm just going to take this expression that we found for L earlier, this thing right here, and I'm going to combine it with our formula for the length of this line segment, which we have right here. So when I put this together with this, the formula for L is a limit as n goes to infinity of the sum, I equals 1 to n, of this. And in for this line segment, the length of this line segment, I'll sub in this. So I have the square root of 1 plus f prime of xi star. Don't worry what xi star is, it's just some number. We don't really know what it is, but we don't care. Times delta x. All right, so now I need you to use your imagination. Think about this thing as its own function, say g of x. Then what this expression looks like is it looks like the limit as n goes to infinity of a sum, I equals 1 to n, of g of xi, I'll say xi star, times delta x. Now squint your eyes. You realize that this thing right here is exactly our definition of the integral. So that this is exactly the definition of the integral from a to b of g of x dx. So what we've figured out is that this thing in disguise is really just an integral. So let me write down our almighty formula for arc length. It will be now the integral from a to b of, let's see, this function, square root 1 plus f prime of x squared dx. So this is so important, I'll put a box around it. This is what we're hoping to find. This is a formula for arc length. So L is the arc length of the curve from the point x equals a to the point x equals b. So it's the length of this, and this is our formula for it. So this is a pretty complicated integral. The integrand is the square root of 1 plus the derivative squared. Okay, but you need to have this memorized for the AP test. So next I will erase the board and show you one example of how to use this in practice. So here's my example for you. Find the length of the curve y equals x to the 3 over 2. I graphed it right here from the point 0, 0, the origin, up to the point 1, 1, which is right here. So we're trying to find the length of this green piece right here. So first thing we'll do is we'll use our formula for arc length. So the arc length, L, is the integral from a to b. So a is at x value 0, b is at x value 1 of square root of 1 plus the derivative of the function. So f prime of x squared dx. You need to know this formula. So what is the derivative of this function? So if that's your y prime, we'll use the power rule, is 3 over 2 x to the 1/2. So you might imagine that because this is such a hard integral, it's going to get ugly, and it will. This is harder than a normal integral problem because you have a square root, you have a derivative, and you have a square. Okay, so let's stick this in here. So this is the integral from 0 to 1 of the square root of 1 plus the derivative squared. And when I square this thing out, I get 9 over 4 x dx. Okay, how are we going to solve this sort of integral? Let me make a u sub. So I want to let u be this whole mess inside. So u will be 1 plus 9 over 4 x. Then du is just going to be 9 over 4 dx. Can you see down here? Yeah. So I'll put the sub in. I'll get that this integral is now the integral from, well, the 0 and 1 are still x values. So I'll write it like this so you know that they're x values. I have the square root of u, and dx now becomes 4 over 9 du. Okay, that's a little bit better. I can kick this 4 over 9 outside. And the best way to think about the square root in calculus is u to the power 1/2. So now I'll use power rule. So this is going to be 4 over 9. The antiderivative of this will be, what, 2 over 3 times u to the 3 over 2. And this is between x equals 0, x equals 1. So now I need to write u back in terms of x. So I'll use this substitution down here. So this is the integral, let me simplify this. So it's 8 over 27, 1 plus 9 over 4, x, between 0 and 1. I can get rid of the x equals because now this is x values and these are also x values. When I plug in 1, I'm going to get something sort of hard. Where did the 3/2 go? It's right there. So I'll plug in 1. Let's see, I get 8 over 27, which I'll pull outside of everything. I plug in 1, I get 13 over 4 to the power 3 over 2. When I plug in 0, I'm just getting 1 to the power 3 over 2, which is just 1. So you see I'm using fundamental theorem here. Okay, how do we simplify this? This simplifies to, I'll write it down here, 8 over 27 times 13 root 13 over 8 minus 1. And if you want to make it a little bit cleaner, you could write this as 13 root 13 minus 8 over 27. So that's the final answer. Now you might be saying to yourself, what am I doing to you? This is brutal. Look at these numbers. It's really hard, it's really ugly, but believe it or not, this is one of the easiest examples. So it's hard to find functions that make this a nice integral. There's really only a few of them. So you will have a quiz on this video. So for the quiz, you need to know this formula, you need to know something about how we got it, and you need to be able to do an example. So see you in class.